Okay, so good morning, all of you. Today we are going to discuss in this particular lecture. We are going to discuss about different types of physical vapor deposition. Okay, and last lecture you got the idea regarding this physical vapor deposition technique. Okay, so last lecture we have discussed the uh, several types of the different deposition techniques. Okay, just for the introduction purpose that we have seen, or maybe we can call surface modification techniques, which we will discuss further also. But in this particular lecture, we are going to discuss only about the physical vapor deposition. In detail, we are going to discuss. So first, before going to start this, let us know that what is this PVD, physical vapor deposition, or maybe physical vapor deposition technique you can call actually, or you can call method. Okay, so now this total entire topic I have divided into two parts. In the part one, we are going to discuss the introduction to this physical vapor deposition. Then we'll see the classification of this PVD. Okay, and in that subtype, we are going to discuss that thermal evaporation, then electron beam evaporation, reactive and activated reactive electron beam evaporation. Okay, and in the part second, we will discuss the further subtypes of this PVD. Okay, so introduction. So, as I have mentioned already that this one kind of method by which physical ejection of the material, ejection means all the spraying you can call, uh, or just coating the material, and upon here we are using some molecules. Okay, so that ejection of the material and some molecules, hence that convection, or we can call the molecules of that nucleation of this atoms molecule. Okay, so that we have to eject that material onto a substrate. Okay, that means from this particular line, you can see in this diagram also. Okay, in this diagram also you can see. Now again, if you see here, line is there. So from this particular line, we can get that we are having the certain kind of base, or maybe that a certain kind of material we are agitating by maybe some laser, or maybe some electron beam, or maybe some current, or maybe some thermal, and that is releasing some kind of atoms, or maybe the molecules, or maybe some kind of plasma metals. Okay, so you can see there from this line. Okay, so from this line, here, as we have the source metal means all our base metal. Okay, and that we have to etch it. Okay, by means of laser, or some electron beam, or maybe current, or maybe thermal. Okay, and that is releasing some kind of atom, or maybe the molecule, or maybe some kind of plasma material. And then when we are using this certain kind of vapor gases, maybe, or may not be, then that material, or maybe that ions, okay, and that molecules can deposit on this substrate. ओके ऑन दिस सबस्ट्रेट म्हणजे काय तर हे आपला सरफेस सॅम्पल जे दाखवतो तो सबस्ट्रेट झाला ओके सो that substrate which we are going to modify okay so in a basic term just simplify we are doing the coating by using any kind of atoms or molecules or maybe the plasma into the vaporized condition into the vaporized condition okay so what are the vapor phase material is there no so that can consist of the your ions or plasma and is often chemically reacted okay, is often chemically reacted with the some gases which are introduced into that vapor and it is called that reactive deposition okay to form a new component okay so from this particular line again you can see that same figure so from that particular line we can understand that whatever the gas we are introducing maybe it can react with that ions or molecules or maybe it can simplify the inert one for or to help that homogeneous coating of that particular metal base metal onto the your substrate itself okay then this process can be applied okay now if you talk about the application now then this process can be applied to various kinds of materials like ceramics polymers metals and alloys composite etc okay so here is that here is just a simple thing okay now this our you can see that yellow color okay so now that is our metal which we are going to substrate that source metal and which we are going to modify and this one or maybe that rather we can say that substrate and this is the that substrate is the that yellow part and that what are the metal ions or maybe some kind of metal which we are going to put on the that top side top of our substrate no so that base metal or the source metal we have to make into the vaporized form okay so here we are keeping our metal then either by giving heat okay that here means the that source metal so here we are keeping our metal and then we are giving the heating by giving heat or maybe some kind of electron beam or maybe laser beam or maybe some kind of other energy and that metals are we are exiting that metals and then metal ions will get so these metal ions slowly it can deposit it on this substrate itself okay so this is a simple fundamental behind this physical vapor deposition okay so here I have written that vapor phase metal can consist of ions or plasma and is often chemically reacted with the gases which are introduced into the that vapor so it is called a reactive deposition okay now you can see here we have the different subtypes of this physical vapor deposition so here I have given the classification of pvd okay now we are going to discuss this about this classification of pvd or maybe physical vapor deposition process so there are several types of this classification okay that are available in terms of that how we are going to modify those samples that means the substrate surface how we are going to agitate how we are going to agitate that material or maybe how we are going to do the coatings or maybe what terms of energy just we are using to agitate those material and do how we are doing the coating over the that substance so depending on that here classification we have made so first one is called you can see thermal evaporation method first one is the thermal evaporation method okay so and the second one is called electron beam or maybe e-beam evaporation method so these are the subtypes then reactive activated reactive oblique activated reactive electron beam evaporation. Okay, here also I want to mention that whatever the classification or whatever the slide materials I am using, also all I have collected from the surface engineering course. So due to that, you might be thinking that this material is somewhat heavy to understand. Okay, but as a part of syllabus or as a just coating technology, we should go in detail also. For that purpose, I am teaching in detail. Okay, so then third is a reactive or activated reactive electron beam evaporation. Okay, then we have the splattering, then filtered cathodic arc deposition. This is again the subtype of the our PVD technique. Then ion plating is there. Okay, and last one is the pulsed laser deposition. Okay, so here we can see that total 7 numbers of classification are available regarding this PVD method. Okay, so first we will discuss in detail about the first, that is thermal evaporation. So a basic question arises that what is this thermal evaporation means. So from the name itself you can understand that we are giving certain kind of heat to the source material. Source material means what? Our base material which we are going to deposit on the substrate. Correct, that is called source material. So from the name itself we understand that we are giving certain kind of heat to the source material so that it can agitate due to that temperature of the heating, or maybe the or that agitate due to heating, and then it can release the atoms or the molecules, and then it will directly that atoms and the as well as that molecules and can go onto the your substrate. Okay, and that process will occur slowly. Okay, so slowly it will deposit onto the top of the your substrate. So here also you can see diagram. Okay, so you can see in the diagram. So here the one thing, or I can say beauty of this technique is that it is totally controllable process. Okay, so what about the thickness we are going to achieve, that we are going to discuss again. This thickness we can achieve easily, okay, on that those material. So a thermal evaporation process, this type uses this here thermal evaporator uses, and electric resistant heater also is used for what purpose? To melt the source material, and you can rise its vapor pressure to its useful range. Okay, so sometimes what happen, we are using certain kind of heating element, or maybe the heating coil, and then that heating coil is giving the thermal environment by which your source is coming to the vapor form, and that vapor is deposited onto your substrate, or maybe the metals, or maybe the ceramic, or maybe the polymer. Okay, now here what are the thermal energies there, no? So that thermal energy is imparted to your atoms. Okay, in a liquid or the solid source, so that it can efficiently evaporate that. So evaporation is taking place in vacuum, and generally we are using the high vacuum, because otherwise what will happen if we do not use this vacuum, no, or maybe we do not use a certain kind of inert gases, maybe that vaporized material. So if we do not use, no, then maybe that vaporized material can be react with the environment oxygen, or maybe the moisture, and it can form a new materials, or maybe the some unuseful material also. So to avoid that such a reaction with the environment, we have to use the inert gas or vacuum. Okay, so here vacuum chamber is required. Whatever you are seeing, no, that dome shaped, it is called vacuum chamber. Okay, so whatever the evaporated particle are there, no, so that can travel directly toward the deposition target without colliding with the background gas. Okay, because we are using the vacuum, and films can also be evaporated using the multiple source. Okay, films can be evaporated using multiple source. So from this particular figure you can see, which is I have shown in the slide. So you can see here, you can understand that we are giving certain source over there, and then we are doing for the degassing, we are having this coating onto the that wall, so that that heat cannot go outside. Okay, so this is our substrate material. Okay, here which I have shown, that substrate, you can see on that substrate we are going to do the coating. Then we are agitating these materials by means of any kind of filter. That means this one. Okay, we are agitating these materials by means of the any kind of filter, or maybe electrical coil, or that so that this can form vapor, and that vapor directly can deposited onto the substrate itself. Okay, so you can see this diagram also. Okay, okay. So now from this we can see that there are several thermal depositions. Okay, and that is accordingly to the input energy which we are using. So you can see here the first that several thermal evaporations are there, no, accordingly input energy. So in that, first is the direct resistance heating is there, then indirect resistive heating is there, then inductive heating, and then laser ablation or laser evaporation. So these are the types of this thermal evaporation. In detail I am telling. Okay, just so we should know that names. Okay, no need to go for in detail. So as I have already mentioned that there are different types of source or energy. So it depends on how we are going to give the energy. Depends on upon that we are doing the nomenclature of different heatings and different thermal evaporation methods. Okay, so again in detail I will discuss here. You can see. Okay, so in this direct first one, no, evaporation material, it directly evaporated by high electric current. So it is called direct resistive heating. Then in case of second, that is indirect resistive heating, no, heating. So here evaporation material is put into the container. It is called the that board. Okay, and the spiral wire or the ribbon or the crucible is used for that heating. Then induction heating. So here evaporated metal is heated by high or low frequency induction, and that evaporated metal has to be conductive in case of the inductive heating. And then third one is the fourth one is the laser ablation or the laser evaporation. No, so here the continuous interaction of laser radiation will be there with the matter, and it can lead for the or to the laser, sorry, to the thermal evaporation. Okay, so this is the in short about this subtypes. Okay, no need to go in detail about this. Okay, now what are the advantages of this subtype of our PVD, that is thermal evaporation? So first one is called, you can see that is this process is very simple and cheap method. काय करायचं, फक्त आपल्याला हिटिंग द्यायचे सोर्स मटेरियलला आणि वेपराइज्ड फॉर्म मध्ये आपल्याला डिपॉझिट करायचं. सो दिस इज व्हेरी सिम्पल अँड इट इज चीप मेथड. and here less surface damage of the your substrate. Okay, here surface damage of the that substrate is less, but here excellent purity will get of your film. We are getting excellent purity of the films. Okay, sorry, films, correct. Because there is no direct method, there is some direct method and there is some indirect method also. So anyhow we are not going to harm our target material, that is the substrate. So pure, we'll get the excellent purity of the different. So just we are giving the energy in this method, just we are giving the energy to the your source material, so that source material can come into the vapor form and simply it can deposit onto the target material, or we can call substrate material. So that is simple funda in this turbine evaporation process. Okay, then there is certain kind of disadvantages are also there. Okay, so in that, as I have mentioned, that it is limited to low melting point metals. Then we are getting poor density and adhesion. Okay, because we are giving certain heat to the particular metal. So due to that, uh, low melting point, sorry, poor density will be there and adhesion. Now, next disadvantage is that if the melting point of the precursor material, okay, or source material is too high, no, then it is very difficult to make them into the vapor form. Okay, so not only that, that directly gas is coming onto the substrate, but we have to convert into the vapor form first, and then we have to direct towards the or onto the substrate. So this it depends upon the surface chemistry of that particular target material. So if the target material is a little bit sticky, or maybe there is some kind of oil, or maybe that glaziness is so if there is that sticky or glaziness is, so that time it will absorb, so automatically that material will deposit onto that surface of the uh, that film, sorry, surface of the that substrate, but there will not be any bonding or maybe addition in between these two. So then it is not possible to operate. Next disadvantage is that it is not possible to operate that dielectric metal or filament, because it limits the amount of metal that can be deposited. Again, step coverage is more difficult to improve. Okay, so there are a lot of disadvantages also are possible here. Now the if you talk about the optimizations, so then optimizations that in that purity of the film, it depends on the purity of the source material. Okay, what are the films which are which we are getting films of that coating, no? So that purity is depend on the source material purity, and the quality of the vacuum in case of the films, the thickness of the film, so that will vary according to the geometry of the chamber also. Okay, then the thing is that what about the source material, or maybe the that precursor material we are going to take that, so that will depend on the purity. If that metal itself impure, then with that metal some impurity also will come into the vapor form, and that will deposit on the substrate, so that will not get the exact property whatever we want on the our substrate surface. So then again, in case of the films, the thickness of film vary according to the that sorry, according to that geometry of the chamber. Okay, now again Now, how that it will varies according to geometry, because it depends upon the vacuum, correct? So if the sample size will be more, then automatically chamber size will be more, and accordingly, because we need a certain constant vacuum for doing this kind of modification. So then we need a, sorry, that modification will depend on that vacuum also. Now let last part is the application. What are the application? So evaporation of metal, alloys, semiconductors, insulators, etc. We can do with this method. Again, that gold plating machines, for that purpose we are using this thermal evaporation, then thermal insulation coating. So this is the common applications generally we can use uh, in different field. Okay, now next one is the, now we are going to discuss the this about the electron beam evaporation, electron beam evaporation or e beam evaporation. So from the name itself, again we can understand that here we are using electron, and then that electron we are bombarding onto the source materials or maybe the precursor materials, and then that precursor uh, or material is released or is releasing certain kind of ion or maybe the molecules or maybe the plasma, and then that is directly depositing uh, onto the your base material or maybe the your substrate. Okay, so you can see here diagram that electron beams are used. Okay, I repeat, from name itself we can understand that here we are using the electrons, and then that electron we are bombarding on the source material or maybe the precursor material, and then that precursor material is releasing some certain kind of ions or maybe molecules or maybe the plasma, and then that is directly depositing onto your substrate. Okay, so this is a electron beam evaporation. So here you can see in this diagram, here is a target anode, and that is bombarded with the electron beam, okay, which is given by a charged tungsten filament, okay, under high vacuum. Here at bottom you can see we have the target anode, and that is bombarded with the electron beam which is given by the charged tungsten filament under high vacuum. So here we are using one anode materials and other one is the cathode materials. So here anode is your source or maybe the precursor, and cathode is your that substrate. So we are hitting or maybe bombarding our anode material by the electron, and then we are agitating those materials, and then they are releasing certain kind of atoms or maybe molecules, and that is depositing onto the cathode, means the your substrate. Okay, maybe your substrate. 1 minute. स्क्रीन शेअर होऊन अवघड झाली. एक मिनिट, कारण की ते नेटवर्क इश्यू मुळे स्क्रीन शेअर व्हायचं थांबलंय. एक मिनिट. अच्छा. Okay, okay. Sorry. I will once again I repeat. लक्षात नाही माईक ऑफ झालं. Okay. So I was talking about the third process, sorry, sub type of the PVD, that is reactive and activated reactive electron beamers. So actually this subtype, it is a combination of our thermal evaporation is first type, and the second is the electron beam evaporation. It is combination. Now the purpose of this reactive and activated reactive electron beam is that certain refractory oxides and the carbides undergo fragmentation during the your electron beam evaporation, and it resulting in a stoichiometry which is different from the initial material. Okay, and to overcome this situation, reactive activated reactive evaporation are employed, and here both electron beam and thermal evaporation processes are used for this reactive and activated reactive deposition purpose. Okay. So firstly, I will talk about the this reactive type. Okay, so what is reactive types? So in this process, a reactive gas generally, that means oxygen, nitrogen, hydrocarbon is introduced. Okay, so in this process, reactive gas are introduced into the chamber. Okay, uh, while metal is evaporated. Okay, and when the this thermodynamic condition are met, no, then metal atoms, it will react with the gas in that vicinity of the substrate. Okay, for our purpose to form the film. So here we are using the gas as well as the atoms togetherly to do the that coating onto the metal or maybe on the your substrate. Okay, so here is the that in this diagram I have shown that here is the technique. Actually we are using certain kind of aluminum, where or there we are using oxygen gas. Okay, so aluminum is the your that material, and gas is that oxygen gas. So it is making the aluminum oxide or maybe that Al2O3, then that Al2O3 is coated on your substrate material. So aluminum and the oxygen gas both are mixing together, and they are doing one kind of chemical reaction which is forming the Al2O3, and then that Al2O3 is depositing on the substrate. So it is called a reactive type. Okay. Then next is called next one is the activated reactive type, or maybe the in short called we are calling it as a capital ARE. Okay, ARE. So here in this process, actually this process is twofold. Okay, so generally it is divided into two steps to enhance the reaction efficiency through the activation of the reactive gas that are necessary, that active gas that are necessary for uh, deposition of that compound film. Okay, so to modify the that what are the growth of the kinetics, and hence that structure morphology of the deposit, uh, we are using this activated reactive. So here actually plasma are used to activate that reactive gas. Okay, to activate that reactive gas, plasma is used. Okay, and it's the operation force, maybe either e beam source or maybe electron beam, or maybe some kind of resistant heating source you can use. So recently developments in this ARE process, no, actually are to produce the vapor species, then confinement of your operation techniques, and the development of modified. that what are the modification in the plasma excitation geometry. So for that purpose you can use. Okay, once again I repeat. Okay, सरफेस कोट सॉरी कोटिंग टेक्नॉलॉजीचा टाईप म्हणजे फिजिकल वेपर डिपॉझिशन. त्यानंतर आपल्याला हे सब टाईप आपण इन डिटेल मध्ये चाललोय. ओके, परीक्षेत इन डिटेल मध्ये कोण विचारणार नाही, पण जस्ट फॉर नॉलेज पर्पज आय एम शेअरिंग. ओके, हे थोडं जड आहे अंडरस्टँड आय नो. ओके, पण तुम्हाला माहित पाहिजे म्हणून मी जस्ट सांगतोय. हिअर ऑल्सो आय हॅव मेन्शन applications of this activated reactive type process. So we can make titanium dioxide, and that we can coat. Then silicon dioxide as optical coating we can use. Then a manufacturing of carbide nitrates means that also that titanium carbide, titanium nitrate, which can be used for coating of the some kind of tool materials, or maybe the cutting tool materials. Okay, then here we can use some kind of inert gas. Okay, sorry, some kind of insert, not inert gas, inserts. Generally we can using for the cutting tools, because as we know that if we want to make some cutting tool by any kind of or this kind of material, then it is very expensive. So what we do generally, we are going to use cutting tool made up of the HSS, and that means high speed steel, and then tip of that tool we can change easily. We can calling it as an insert. Okay, so that material is made by the titanium carbide. Okay, maybe the titanium nitride also. So we can do that tip, that whatever image I have shown here, no. So that carbide coating we can do with this activated reactive type. Okay, now let us discuss the next part, that is the spluttering. Okay, next is sub type of the PVD. One minute. Okay, so next is the splittering. Actually, this is a common method, or maybe that is easily available method we can call. And nowadays means we're excessively using this splittering techniques everywhere. Okay, so what are the steps for this splittering process? You can see in the slide also. First one is you how to put our target material, and then substrate is placed in a vacuum. Okay, you can see in the figure also. So this is your vacuum in the figure, where you can putting your substrate, and then you are putting your target material or maybe the source material over there. Then you are using certain kind of plasma over there. If voltage is applied between the target and the substrate, if so there should be some kind of potential difference will occur, and in between that your cathode and in between if potential difference will occur, no? So plasma is created by ionizing that splattering gas, and generally chemical inert heavy gas like argon is used as a splattering gas. So here we are using the inert gas like argon and making this gas into the plasma form. Okay, पिवळ्या कलर तुम्ही बघू शकता. Then that plasma actually it is depositing onto the your substrate. Okay, so atoms or the molecules of that target material are ejected into the gas. into the gas form or the plasma due to the bombardment of splattering gas, and ejecting that target material will deposit onto the substrate itself. So simply we are putting certain kind of potential difference in between your cathode and anode, and then we are ejecting certain kind of plasma over there, which is nothing but the directly coming from your coming from using the argon gases, and then that plasma is directly hitting onto your target metal, maybe the source metal, and then due to the some kind of atom or molecule, it is directly coming from the source metal, and it is depositing onto the your substrate metal. So that is called the splattering technique. Okay, so that it is called the splattering technique. So for efficient movement transfer, the atomic weight of the splattering gas like argon or the neon that chromium, then xenon should be close to the atomic weight of the target, otherwise it will be or otherwise it is a little bit difficult. Okay. Okay, then what are the advantages of this process? So here first is the materials having high melting point can be easily splattered, and films by splattering have better adhesion on the substrate, okay, than your evaporative film. Okay, what is the disadvantages? So inner that splattering gases are built into the your that growing film as a impurities, so it can create certain kind of impurities too. Okay, but if we see overall, this splattering technique is good and it is cheap and it is less time consuming process. Okay, so you can see, or you can take 1 minute to read that steps also. Okay, you can take 1 minute and just to read that steps, whatever I have explained. Just read out that what I have written. Okay, now let us go for the next one. So next technique we are going to discuss is called cathodic arc deposition method. So first we have to know that what is the cathodic arc deposition method. Okay, so here actually elliptical arc is used. Here elliptical arc is used to vaporize the material from the target cathode. Okay, to vaporize the material from the target, here elliptic arc is used. Okay, now that target means what? Cathode, and that vaporized material then condense on your substrate, okay, by forming a thin stream. Okay, so here you are using some cathode material. Over there you can see a diagram. So I was talking about the sun. So here you are using some kind of, sorry, some kind of cathodic material. Okay, you can see there. I was mentioned also cathode. Okay, and then you are using the plasma. Okay, so that plasma ions, the that plasma ions will produce the arc. Okay, and that arc is going to the cathode side, so cathode side, and the metal ions, it is going to the your substrate. You can see हे सबस्ट्रॅट आहे आपला सबस्ट्रॅट, तिकडे मेटल आयन्स चालले. ओके, आणि आर्क कुठं चाललं तर कॅथोडचा. ओके, so here you are using some kind of potential difference by using some kind of power supply also. So you are using some kind of high potential difference in between your cathode and the anode material. Okay, so cathodic arc takes a special space, that this place among these all periodic processes because of high ion densities. Okay, so the technique may be it can be matched 90% with the other technique, but here the density of the ion whatever we are getting is more than the other process. So here arc vaporization occurs when a high current, low voltage is passed through the your source material, which is placed between the two electrode, anode and cathode. Then this process produces extremely hard films. So therefore it can be used for thin hard film, super hard coatings, or nano composite coatings. It can be used to deposit the metallic or ceramic and the composite film also. So this technique are more versatile than the other. Okay, I can say here we can use many materials. We can use some kind of hard materials also. So issue faced during or by this cathodic arc process, no, we are getting poor film quality. Okay, again uniformity in thickness, or poor or control, poor repeatability, and that reliability also for production process. We require high maintenance. So these are the that issue regarding this process also. Okay, so once again I repeat about this cathodic arc deposition. Here our electric arc is used to vaporize the material from the target cathode. Target cathode, this. Okay, and that vaporized material then condensed on your substrate, okay, by forming a thin stream. So here you are using some cathode material. I repeat, cathode material over there which I have shown, and you are using the plasma. Then that plasma ions, that arc is going to the your cathode side, and the whatever the metal ions is there, no, it will going toward the your substrate side. So here you are using some kind of potential difference by using some kind of power supply, and you are using that potential difference, high potential difference in between your cathode and your anode. Okay, once again I will give 1 minute to read this. Okay, सिलॅब वन्स अगेन आय रिपीट, सिलेबस मध्ये हे कुठं कॅथोडिक आर्क डिपॉझिशन वगैरे असं कुठं पॉईंट नाही, फक्त काय फिजिकल वेपर डिपॉझिशन. ओके, यू विल हॅव द फुल फ्रीडम टू राईट एनिथिंग अबाउट दिस पीव्हीडी. तुम्ही इन डिटेल मध्ये लिहा, इन शॉर्ट लिहा, नो प्रॉब्लेम. तुम्हाला नोट लिहा किंवा एक्सप्लेन म्हणूनच क्वेश्चन विचारला जाईल. नॉन कन्व्हेन्शनल मशीनिंग हा सब्जेक्ट फर्स्ट टाइम लास्ट सेमिस्टरला बी साठी इंट्रोड्यूस झाला आपल्या युनिव्हर्सिटीमध्ये. ओके, फर्स्ट टाइम इंट्रोड्यूस झाला होता, पण त्याचं युनिव्हर्सिटीचं काही एक्झामच झालं नाही. आता आहे तिथं काही एमसीक्यू बेस्ड आहे, त्यामुळे थेअरी क्वेश्चन पेपर सॉरी थेअरी क्वेश्चन अजून आपल्याला युनिव्हर्सिटी विचारलं नाही. फक्त टेंटेटिव्हली ॲज अ सब्जेक्ट टीचर, ओके, आय विल गिव्ह ॲश्युरन्स दॅट एक्सप्लेन पीव्हीडी और सीव्हीडी टेक्निक किंवा राईट अ नोट ऑन, असं तुम्हाला क्वेश्चन विचारलं जाईल. कारण की युनिव्हर्सिटीने ह्या चॅप्टरला वेटेजच कमी दिलेलं आहे. ओके, नाव सुद्धा बघा की इंट्रोड्यूस टू कोटिंग टेक्नॉलॉजी, फक्त आपल्याला इंट्रो, जसं तुम्हाला मेटलर्जी सब्जेक्ट मध्ये एक लास्ट चॅप्टर पावडर इंट्रोडक्शन टू पावडर मेटल आहे, तसा हा चॅप्टर म्हणू शकता तुम्ही. ओके, नाउ लेट अस डिस्कस द नेक्स्ट, दॅट इज अ फिल्टर्ड कॅथोडिक आर्क डिपॉझिशन प्रोसेस. तुम्ही नाव जर बघितले ना बघा की मागच्या मेथडचं थोडं एक्सटेन्शन असं झालंय. ओके, इलेक्ट्रॉन बीम दॅट इव्हॅपोरेशन बघितलं आपण, थर्मल इव्हॅपोरेशन बघितलं, त्यापुढे काय आहे तर ऍक्टिव्हेटेड रिएक्टिव्ह इलेक्ट्रॉन बीम लेझर. ओके, देन स्प्लिटरिंग बघितलं, कॅथोडिक आर्क. आता कॅथोडिक आर्कचा पुढचा पार्ट म्हणजे काय, फिल्टर कॅथोडिक आर्क डिपॉझिशन. ओके, so here from this name itself we can understand that this is a little bit modified version of the previous one. Okay, this is a little bit modified version of previous one, means the your cathodic arc deposition. So here the filtered cathodic arc process is extensively used to deposit tribological and wear resistant thin film. For what purpose we are extensively using this process? So extensively used for to deposit tribological and wear resistant thin film, and mainly it eliminates the macro particles that degrade the coating performance. So the small size particles, or maybe the same sized particles, rather I can say that all the particles whatever it is depositing onto the your substrate, all particle size are more or less. Okay, so there should not be any mixture of the bigger particle and the that if the particle size will be bigger, then it is very difficult to stick on the substrate material. And not only that, its a surface area will be less. Correct. So there will be the less adhesion in between the coating material and the substrate material if the your particle size is large. So to here that ejecting particles are fed into the your curved duct. Okay, here I got this image I got I think from one of the research paper. Okay, you can see. So here ejected particles are fed into the curved duct. ओके, म्हणजे सोर्स मटेरियल जे आहे आपलं तिथनं जे इजेक्ट झालेले पार्टिकल्स आहे, सो दॅट आर फेड इन टू द कर्व डक्ट. यू कॅन सी दॅट डक्ट. So you can see there is a duct also over there. So through this duct your particle is going through, and then it is falling onto your substrate material. तुम्हाला तुमचं सबस्ट्रॅट इथं बघू शकता, आणि आपलं इथं दिसतंय बघा तुमचं सोर्स मटेरियल. तो इथनं ते जाणार. ओके, so it will falls onto your substrate material, and here So that what are the engineering particles which are fed into that curved duct, no? So that will pass through your duct, and the particles will go through that duct, and then it will fall into your substrate material and steering field, which separate the particles by mass. So the filtering then will be carried out with the help of mass spectrometer. So here there are several kinds of filtering coils are used, which is absorbing the bigger particle size and then only allowing the smaller particle size to go further and to fall on your substrate. So you can see filtering coils. In this case, my filtering coils as well. Okay, they have shown. And then unwanted that micro particles, that means the large particles and the neutral atoms are filtered out by the mechanical filter. Okay, by the mechanical filter also. And coating space is reaching what are the coating spaces that is reaching the substrate are pure ions. Okay, whatever we are getting here, no, that are the pure ions. And the beam of the particle must be rested over that substrate to coat large area which is acceptable uniformity. Okay, so here this is actually a movable one, so that it can cover up the whole area. Okay, if the sample size will be bigger also. Not only that, here is the purity of the coating, it's that we are getting 100%. Okay, and then again it is very easy to take out the impurities from this coating material using this process. Okay. Okay, again 1 minute I will go to just read this data. Okay. Now let us discuss the next one, that is ion plating. Okay. So next one is called ion plating. So again, it is an that atomistic vacuum coating process. Atomistic vacuum coating process where depositing film is continuously or periodically bombarded by energetic atomic size inert or reactive particles. Okay, so here we are not putting any kind of field, we are not putting any kind of electron beam, we are not putting any kind of laser. So here we are using certain kind of energetic atomic size inert or maybe the reactive particles. We are bombarding on to your source material, and then we are doing the coating onto the substrate. I repeat, here we are using certain kind of energetic atomic sized inert or maybe reactive particles, and we are bombarding that particles onto your source material, and then we are doing the coating onto our substrate. So it is also called an ion assisted deposition. Ion assisted deposition, IAD, or maybe the ion vapor deposition, IVD. Okay, so what are the activated reactive evaporation or process is there with a negative bias on a substrate, it is called reactive ion plating. Okay, so it depends upon the source how we are using, or how we are going to use a different source. So using the different source, it is having the different nomenclature, correct? So the source of the deposition atoms can be from a vacuuming operation, filtering or vaporization, or from a chemical vapor procedure also. So from this, there is certain mechanisms are available. So which are that mechanisms of ion plating? So here I have given surface preparation first, right? Then nucleation, and then nucleation and interface formation. And the last is the film growth. So here the source of depositing atom. First, in the evaporation technique, we are having the substrate. You are using certain kind of plasma. You are having the filament. Then directly the material is deposited onto substrate and heat or on the top of the substrate. But here we are using certain kind of target material. So that target material is forming certain kind of plasma, and that plasma can hit the target material. Then from here, some kind of atom or the material and the molecules are directly go, and it can deposit on the substrate. Okay. Now just let us discuss in detail about this ion plating. Here we have some types of subtypes of ion plating processes. So in that we have the pulsed laser deposition. Sorry, that is another. We have the plasma based ion plating is there. Okay. Then accelerated are there. Sorry, vacuum based plasma, vacuum based ion plating also there. Okay, no need to go in detail. So actually we have some disadvantage of this process, or we can call limitation. That is a possibility of that unwanted substrate heating is happening in this process, and also here that some plasma bombardment will be introduced during the process. Okay. Now let us discuss the last one, that is pulsed laser deposition, PLD. Pulsed laser deposition. Okay, or maybe PLD process. So here a high power pulsed laser is focused. Here a high power pulsed laser is focused on a target which is ablated from the ablated to form a that plume of the atom or the molecules, and it will particulate directly towards the substrate. It can work under a controlled gas environment, both your inert gas and the reactive gas. Also, it depends upon the which kind of material we are using to coat. Okay, and I will give the explanation about the mechanism of this process, PLD process. So, mechanism of this PLD process can be expressed in the three steps. Okay, in the three steps. First one is called the interaction of your laser beam and the target. Interaction of your laser beam and target. Then next step is the plume formation, and the last is the nucleation and the growth of your thin films. So simple. Till now we are discussing about the different types of fitting element, maybe electric coil, or maybe a certain kind of laser, or maybe certain kind of electron beam. So here first we are putting our laser beam directly onto the target itself. Then it is creating certain kind of plasma, and then that plasma is depositing onto your substrate material. So that is why it is called pulsed laser deposition. Okay. Now, how we are going to control your laser? Depending on that whether it is pulsed means there will be any on-off mechanism, or maybe there it will be continuous or non-continuous. So it depends upon the what type of source of energy you are using to use. Okay, so some factors that are influence this diffusion rate is called the target material. Also pulse energy of your pulse, then distance from your target to the substrate, the type of gas we are using, pressure in that your chamber, oxygen, that gas or the organ, etc. So that are the some factors also. So here first you are having the target and you are using certain kind of plasma over there. So then that plasma is directly hitting your target metal. Then it is making certain kind of gas, or maybe certain kind of ion, or maybe that's some kind of plasma expansion over there. And then that expanding plasma flow is directly deposited on the substrate, and it is doing the growth of that particular metal. So that is called pulsed laser deposition. Now, what are the benefits of this process over the other film deposition methods? Okay, so you can see here. It is faster response process, again well controlled deposition rate, relatively high deposition rates also. Growth in any environment can be possible. Either you can use a certain kind of rate to gas, or maybe you can use certain kind of filler gas. Also flexible, easy to implement, reproduce the composition of the target. Then you can use for depositing multi-layer films, deposition of highly crystalline films. That means you can make the sandwich structure also. Okay, so coating of one metal, then top of that you are using another metal also. So then top of that you are doing use or going for another metal. That's also possible. So but it is depends upon the as per your requirement. Also there are some disadvantages. So here I have mentioned that high defects or a particular concentration, uneven coverage, not well suited for the large scale film growth, and this clearly does not fit for every application. Okay, plasma laser deposition, it is not fitted for every application. Actually, nowadays generally nowadays we are using onto the window, maybe car window, or maybe that our household window. Okay, simple where at time of raining that water particles not going to penetrate into that window, or maybe that सॉरी, ते काय होते मधनं कुणाचा फोन आला ना, कटत होता, म्हणजे मोबाईल गुगल मीटनं बाहेरच मी पडतोय मोबाईल, आणि पुन्हा ते नाही, मी बघत नाही ना की बा जॉईन झालोय. ओके. Okay, so I was talking about the this PVD summary. Yeah? Up till now, we have covered all the types of the what is mean by PVD, and then sub classification, and then subtypes. Okay. Oh, like message पाठवलाय त्यांना सरांना. Okay. So, and we are discussing in detail about that subtype also. Now let us just take the summary or just summarize this PVD. Okay. So in this physical vapor deposition, except a reactive sputtering deposition process, we are not involving any chemical reaction. Okay, chemical reaction are not involved except for reactive sputtering deposition. Okay, now the main advantage of this PVD physical vapor deposition are, first is that advantage is that a controllable growth of the thin film with the high purity. Yeah? As I told earlier, already, you can eliminate the impurities by using several kinds of the methods, and not only that, you can use the controllable growth depending upon that how much energy you are using to put or where going to put on your target material or maybe the source material. Okay, and another advantage is that ability to control the structural and the morphological properties of the film. So easily you can make the material from hydrophobic to hydro that philic, or not only that, you can make the material which can withstand with the high temperature, or maybe it can easily electric conductive also. Okay, so whatever the properties you want, or you can do it by this method, you can do, and the improvement in the repeatability and the reliability of the your modified substrate. In most cases, another advantage is that in most cases instruments are highly precise as well as the effective. Okay, if you go for this using this process, and the modification techniques can be applied in various fields like manufacturing of semiconductor devices, optical coatings, tribological coating, or aerospace industries purposes also we can use. Okay, so this is about the our today's topic, that is physical vapor deposition. Okay, so I know today's lecture is heavy to understand. Okay, if you will not get that, if you get got today's lecture less than 50%, then also no problem. Okay, if you go through this topic once again or by reading some study material, then also you will get more than 70%. Okay, आणि जेवढं शक्य आहे तेवढं मी मटेरियल ह्या स्लाइड वगैरे मध्ये टाकलेलं आहे. तुम्हाला असं मटेरियल तुम्हाला कुठल्या बुक मध्ये भेटणार नाही, अजून सांगतो. ओके, यू हॅव टू रेफर द some surface engineering book also, but in that book also you will get in detail. Okay, I have one book also that I will give regarding this coating, but in that also you will not get like this combination. आपल्या सिलेबस नुसार ते पार्ट जेवढा मी कव्हर केलाय तो आय थिंक मोर दॅन सफिशियंट आहे, मोर दॅन सफिशियंट. ओके, असंच तुम्हाला पुढं केमिकल वेपर डिपॉझिशन टेक्निक आहे, पुन्हा थर्मल स्प्रेइंग एक आहे, आणि राहिला मेटल कोटिंग. तीनच पार्ट आहेत. एक 3 लेक्चर मध्ये संपून जाईल हा चॅप्टर. कोणाला काय डाऊट नाही, अजून रिपीट करतो. नॉन मशीनिंगच्या कुठल्याही जर प्रोसेस बघितल्या तर ते कसं आपल्याला अंडरस्टँड व्हायला सोपं होतं, कारण की आपल्याला मॅन्युफॅक्चरिंग प्रोसेस सब्जेक्ट झालेला आहे किंवा तुमचं मॅन्युफॅक्चरिंग टेक्नॉलॉजी, ते तुम्हाला मेट्रोलॉजी त्यामुळे तिथं तुम्हाला थोडं ते कनेक्शन भेटत होतं. हे पूर्ण पार्ट हा वेगळा आहे. ओके, सो थोडं डिफिकल्ट अंडरस्टँड व्हायला, बट आय ट्राय my 100% with 100% to explain all these things and to give the 100%. Okay. कुणाला काय डाऊट असेल तर विचारा. आणि ज्याला कुणाला समजलं नाही अजून पण थोडंफार पण समजलं नसेल त्याने प्लीज वन्स अगेन यू कॅन गो थ्रू द what are the lecture I have shared in the last lecture, no, that YouTube lecture. Please go through that. जे आता मी शिकवलं तेच त्या लेक्चर मध्ये शिकवलेलं आहे, फक्त शॉर्ट टाइम मध्ये शिकवलेलं चांगलं. आता फक्त काय सीव्हीडी तर सीव्हीडीलाही आपल्याला एक तास लागेल, म्हणजे केमिकल वेपर डिपोशनला, आणि त्यानंतर थर्मल स्प्रेइंगला 1 तास आणि मेटॅलिक कोटिंगला 1 तास. एक 3 लेक्चरचा सिलेबस आहे. मे बी जास्त लागेल ह्याला मेटॅलिक कोटिंगला जास्त थोडा आहे. And I will share the PPT. Yeah, it's PPT I will share. Okay. Any doubt? Any suggestion? Correction? हा, तुम्हाला गेटला हे नाही बरं का, कोटिंग टेक्नॉलॉजी तुम्हाला गेटला नाही. नॉन कन्व्हेन्शनलचं फक्त पार्ट आहे, म्हणजे दुसरे आतापर्यंत जे 5 चॅप्टर मधलाच पार्ट आहे तुम्हाला गेटला वगैरे. इव्हन तो IASच्या पण एक्झामला आहे, RTOच्या पण एक्झामला तुम्हाला ते नॉन कन्व्हेन्शनल मशिनिंग म्हणून येते. त्यात तुम्हाला कसं की त्यांना एक्सपेक्ट काय असतं की तुम्हाला प्रत्येक ऍडव्हान्स मशीनिंग प्रोसेसचा वर्किंग प्रिन्सिपल माहित झालं पाहिजे. मटेरियल रिमूव्हचं काय ऍक्च्युली प्रिन्सिपल आहे, म्हणजे कुठली एनर्जी वापरली जाते, कसं मटेरियल रिमूव्ह होतं, ते माहित असणं गरजेचं आहे. ओके. I think up to chapter number 3 we have taken our that MCQ test. Okay, so for chapter number 4 and 5 we'll take within this week. ह्या आठवड्यात आपण घेऊन टाकू एक 20 क्वेश्चनच्या 2 टेस्ट ऑनलाईन MCQ टाइप. Okay, so wait 2 minutes. Quickly I will write your roll number. I think except my subject, I'm a metallurgy. All subject syllabus over, I think. Okay, if I'm not wrong. आपल्या होऊन जाईल. नंतर मग ते आपण गेट आणि जे आय एस किंवा कुठल्या कॉम्पिटेटिव्ह एक्झामला जे विचारलं जाते त्यावर आपण मग डिस्कशन चालू करू. माशेलकर नोटेड युअर अटेंडन्स बंदवर. अजून कोण आला आता? खडसरे 38 बार नोटेड. ओके, 1 मिनिट. टाइम आपला टाइम आहे तर 10 मिनिटात एक छोटस व्हिडिओ आपण फक्त बघू. think net मध्ये काय चालत नाही. Okay, so let it be. In the next lecture, we'll start our the new coating technology technique, that is a chemical vapor deposition. So for today's lecture, this part is sufficient. Now you can leave this meeting, no problem. Thank you all of you.